Okay, so you sent over this chapter from a math book, and
Yeah,
you know, I gotta say, like at first glance, it looked a little dry,
sure.
but it's
Right.
polynomials, right?
Right.
And they're really important.
Yeah.
So we're gonna do a deep dive today into polynomials and try to make this
Okay.
like as interesting and like kind of fast and efficient as possible.
Sounds good. Yeah.
So when we say polynomial, like what are we actually talking about?
So a polynomial is basically like an expression, right?
Okay.
It's got variables and numbers in it.
Mm-hmm.
And the important thing is the variables can only have like those nice whole number powers,
Okay.
like 1, 2, 3, 4, and so on.
Got it.
Like, no fractions, no negatives, no weird stuff.
Okay.
Just straightforward.
Like x squared, x cubed.
Exactly. And the book gives some good examples here.
Mm-hmm.
Like, we've got 4x plus 2.
Okay.
Simple one.
Yeah.
Right? The callus is just to the power 1, even though we don't write the 1. Then there's 2y squared minus 3y plus 4.
Mm-hmm.
So now we've got y squared and y.
Right.
Another one, 5x cubed minus 4x squared plus x minus 2.
Okay.
So, x cubed, x squared, x to the first power.
Yeah. Yeah.
And then one more, slightly more involved.
Okay.
7u to the 6th minus 4 23rds, u to the 5th plus 4/8, u to the 4th minus 2.
Okay. So that's a mouthful.
Yeah, a little bit, but
Yeah.
the key is the highest power there is 6.
Got it.
Right.
Okay. So we've got like basically terms with those powers of x, like you said, x squared, x cubed,
Yeah.
whatever, connected by pluses and minuses.
Right.
And then, multiplied by just regular numbers.
Exactly, the coefficients.
Right. The coefficients. Okay.
Yeah.
Now the chapter also goes into what a polynomial is not.
Right. It's always good to know like where the boundaries are.
Yeah. What to avoid.
Right. What not to do.
What are some of the no-nos?
Okay, so one example they give is 1 over x minus 1.
Okay.
Big problem here is that x is in the denominator. Like you can't have a variable down there.
Got it.
Another one is the square root of 2x plus 3.
Okay.
So that square root, that's the same as having a power of 1/2,
Oh, right.
which is not a whole number.
Yeah, it's got to be a whole number.
Exactly. And then last one they give is 1 over x squared plus 2x plus 3,
So
variable in the denominator.
can't have it.
Nope.
Okay, so keep the variables out of the bottom of the fraction.
Right.
And those xx squared, x cubed, keep it simple.
Exactly.
Okay, now the book starts talking about the degree of a polynomial.
Mm-hmm.
What is that telling us?
So the degree is just the highest power you see in the whole expression.
Okay.
Because like, remember, 4x plus 2.
Yeah.
Highest power of x is 1. So degree is 1.
Easy.
2y squared minus 3y plus 4.
Okay.
Highest power is 2. So degree is 2.
Makes sense.
5x cubed minus 4x squared plus x minus 2 degree is 3.
Okay.
And that long one with the to the 6, that was degree 6.
Okay, so the degree is just the highest power.
That's it.
And what's that useful for?
Well, it helps us, like, categorize polynomials into different types.
Okay, so like I remember hearing like linear and quadratic and cubic.
Exactly.
Are those based on the degree?
Yeah, so a polynomial with degree, one that's a linear polynomial.
Mm-hmm.
And the book gives us a bunch of examples like 2x minus 3, 3/5, x plus the square root of 2.
Okay.
Even y plus the square root of 2.
So it doesn't have to be x, it could be any letter.
Yeah, any variable.
Okay.
Other examples, 11/2, x minus 1, 3z, plus 4, 2 over 1u plus 1/3.
Okay, so they all look a little different, but
Yeah, but they all have that same, like, core idea.
the variable is just to the power of 1.
Exactly.
Okay, got it.
And then we move up to degree 2. Those are called quadratic polynomials.
Okay, so quad for squared.
Exactly.
Okay.
The general form is usually written as x squared plus bx plus c,
Mm-hmm.
with the important condition that a can't be 0.
Right, because then it would just be linear.
Exactly. Some examples here. X squared plus 5 minus x squared, y squared minus 2x squared minus 3x plus the square root of 5.
Okay, got it. So those are all quadratic.
Yeah.
And then what about degree 3?
Degree 3, those are the cubed.
Cubics, okay.
Yeah. So x cubed plus bx squared plus cx plus d,
Mm-hmm.
it can't be 0.
Right.
Examples are 2 minus x cubed, just plain x cubed square root of 2x cubed plus 1/3 x squared.
Okay.
And 3x cubed minus x squared plus x minus the square root of 5.
Okay, so the key there is that x cubed.
Yeah, that's the highest power.
Got it. Okay, so we got a handle on like what polynomials are, how we classify them by degree.
Yeah.
Now the book moves into talking about the value of a polynomial.
Right.
What does that mean?
So basically, you've got your polynomial, let's call it p of x.
Okay.
And you want to know, like, what's its value at a particular number.
Okay.
So let's say x equals k.
Mm-hmm.
You just replace all the x's in the polynomial with that number k,
Okay.
and then do the math.
Okay, so it's like plugging in a number for x.
Exactly.
Okay.
So the book uses this example P of x equals x squared minus 3x minus 4. And let's say we want to find its value when x is 2.
Okay.
So we just plug in 2 everywhere we see an x.
Right.
So it becomes 2 squared minus 3 times 2 minus 4,
Okay.
which simplifies to 4 minus 6 minus 4, which is negative 6.
Got it.
And similarly, if we want the value when x is 0, we plug in 0. So 0 squared minus 3 times 0 minus 4, which is just negative 4.
Okay, so it's like taking a snapshot of the polynomial
Yeah, a good way to put it.
at a particular x value.
Right.
Okay, and then this leads us into the idea of zeros of a polynomial. This seems like a really important concept.
Yeah, it's pretty crucial.
What exactly is a zero?
So a 0 of a polynomial p of x, it's a number.
Okay.
Let's call it k again.
Okay.
That when you plug it in for x, it makes the whole polynomial equal to 0.
Okay.
So in other words, p of k equals 0.
Okay, so it's the x value that makes the whole thing 0.
Exactly. And the book keeps using our example p of x equals x squared minus 3x minus 4.
Okay.
And they show that if you plug in negative 1 for x, you get negative 1 squared minus 3 times negative 1 minus 4.
Right.
Which is 1 plus 3 minus 4, which is 0.
Okay.
So negative 1 is a 0.
Got it.
And similarly, if you plug in 4, you get 4 squared minus 3 times 4 minus 4,
Yeah.
which is 16 minus 12 minus 4, also 0.
Okay.
So 4 is also a 0 of this polynomial.
Okay, so we've identified the zeros.
Yeah.
But how do we actually find them?
So how you find the zeros, it really depends on the degree of the polynomial.
Okay.
For a linear polynomial x plus b,
Yeah.
finding the zero is pretty easy.
Okay.
So if k is the 0, then by definition, ac plus b equals 0.
Right, because it's a 0.
Right, and then you can just rearrange that equation to solve for k.
Okay.
And you get k equals negative b over a.
Okay, so for a linear polynomial, the 0 is just
A negative b over a.
easy peasy.
Yeah, just remember that formula.
Okay, now the material you sent spends a lot of time on like the geometry of these zeros.
Right.
Like what they look like visually.
Yeah, it's a really nice way to understand them.
So let's start with linear polynomials again.
Okay.
What does a 0 look like on a graph?
So if you graph a linear polynomial, y equals x plus b, it's always going to be a straight line.
Right.
And as long as a key is not 0, that line is going to intersect the x-axis at exactly 1 point.
Okay.
And here's the key, the x-coordinate of that intersection point.
Yeah.
That is the 0 of the polynomial.
Oh, okay, so it's where the line crosses the x-axis.
Exactly.
Okay.
And the book uses the example y equals 2x plus 3.
Right.
We found earlier that its 0 is negative 3 halves.
Yeah.
And if you were to actually graph that line, you'd see it crosses the x-axis at negative 3 halves 0.
Okay, cool. So it all ties together.
Yeah, it's pretty neat.
All right, what about quadratic polynomials?
So those are the ones with degree 2.
Right.
Yeah.
Y equals x squared plus bx plus c. Their graphs are parabolas, right?
Yeah, parabolas which can open up or down.
Right, depending on the a.
Exactly.
Okay, so where are the zeros in all this?
So the zeros of the quadratic, they're the x-coordinates
Okay.
of the points where the parabola intersects the x-axis.
Okay.
And now a parabola, it can interact with the x-axis in a few different ways.
Okay.
And that leads to different numbers of zeros.
So the book mentioned 3 possibilities, right?
Yeah, 3 main cases.
Can you walk us through this?
So first case, the parabola just cuts right through the x-axis at 2 different points.
Okay.
So in that case, the quadratic has 2 distinct real zeros.
Right, the 2x values where it crosses.
Exactly. Second case, the parabola just touches the x-axis at 1 point
Okay.
and then bounces back.
That doesn't go through.
Yeah, it just grazes it.
Okay.
And this happens when the 2 zeros are actually the same value.
Okay.
So the book might call them 2 equal zeros or coincident zeros.
Right.
So you essentially have 1 distinct 0, but it kind of counts double.
Okay.
And then the third case is when the parabola is like floating above the x-axis
Okay.
or entirely below it,
So it never touches.
never intersects.
Okay.
So in that case, the quadratic has no real zeros.
Got it.
And the book has these nice figures.
Yeah, I was looking at those.
Yeah, figures 2.3, 2.4, and 2.5,
Yeah.
just to visually show these 3 cases.
Super helpful.
Yeah, and the main takeaway here is that a quadratic can have at most 2 zeros.
Okay, so it can have 0, 1, or 2.
Exactly.
Okay, what about when we step up to cubic polynomials?
So degree 3.
Yeah, their graphs get a little more complicated, right?
Yeah, a little more wiggly.
Yeah, wiggly.
So the graph of a cubic, it can intersect the x-axis at most 3 points.
Okay.
And just like before those x-coordinates where it intersects,
Yeah,
those are the zeros.
got it.
The book has this example, y equals x cubed minus 4x.
Okay.
And if you factor that,
Mm.
you get x times x squared minus 4,
Yeah.
which is x times x minus 2 times x plus 2. So its zeros are negative 2 and 2.
Okay.
And figure 2.6 in the book shows the graph.
Yeah.
And it's crossing the x-axis at those 3 points.
Right, at -2 and 0 and 2.
Exactly.
Okay.
And they also give a couple other cubic examples.
Yeah, like with slightly different looking graphs.
Right, so there's y equals x cubed,
Mm-hmm.
which it just touches the x-axis at x equals 0.
Okay.
So it has one real 0, x equals 0,
Right.
but it kind of counts triple.
Oh, because of how the graph looks.
Exactly.
Okay.
And then there's y equals x cubed minus x squared,
Right.
which factors as x squared times x minus 1.
Okay.
So it's got zeros at 0 and 1,
Okay.
but 0 kind of counts double in this case.
Right.
And figure 2.8 shows that graph.
Yeah, it's touching the x-axis at 0 and crossing it at 1.
Exactly.
Okay. Yeah.
And these examples, they really show that general principle
Mm-hmm.
that a polynomial of degree n,
Right.
it's going to have at most n zeros.
At most in zeros. Okay. And then there's example 1 in the book where they give you a bunch of graphs.
Oh, yeah.
And you have to just say how many zeros.
Based on the picture,
Yeah.
right? So it's just like a visual exercise.
Yeah, like connecting the dots.
Yeah. So in each graph in figure 2.9,
Yeah.
you just count how many times the curve crosses or touches the x-axis.
Right.
And that's how many zeros it has.
Simple as that.
Yeah. So like if it crosses once, 1 0.
Yeah.
If it crosses 3 times, 3 zeros.
Okay.
And in case VFE, the graph crosses 4 times, so 4 zeros.
Okay, cool. So the geometry really helps.
Yeah, it makes it a lot more intuitive.
Yeah, absolutely.
Yeah.
Okay, so now the book gets into this whole thing about the relationship
Mhm.
between the zeros and the coefficients of a polynomial.
Right.
So, like, how are the numbers in the polynomial itself
Yeah.
connected to its zeros?
It's a pretty neat connection.
Okay, so let's start with quadratics again.
Okay.
So we've got our general form, x squared plus bx plus c.
Mm-hmm.
And let's say the zeros are alpha and beta. So the book says we can write this polynomial in factored form,
Right.
like x squared plus bx plus c equals k times x minus alpha times x minus beta,
Yeah.
where k is just some constant.
Mhm.
And then if we expand the right side,
Right. We multiply it all out.
yeah,
We get k times x squared minus alpha plus beta times x plus alpha times beta,
okay,
which we can write as k squared minus k times alpha plus beta times x plus k times alpha times beta.
mm-hmm.
And now we can compare the coefficients.
Right, like the numbers in front of the x squared, the x, and the constant term.
Exactly. So we see that a equals k,
Right,
b equals negative k times alpha plus beta,
right.
and c equals k times alpha times beta.
Okay, so now we have these relationships.
Yeah, and from those,
Yeah.
we can get two super useful formulas.
Okay, hit me.
So the sum of the zeros, alpha plus beta,
Mm-hmm.
that's equal to negative b over a.
Okay, negative b over a.
Yeah, and the product of the zeros, alpha times beta,
Yeah.
that's equal to c over a.
Okay, so c over a. So we
Mhm.
can get those directly from the polynomial itself.
Exactly.
Okay, and then the book has some examples of this in action, right?
Yeah, so example 2 looks at the quadratic x squared plus 7x plus 10,
Okay,
which we can factor as x plus 2 times x plus 5.
right.
So the zeros are negative 2 and negative 5.
Okay,
And let's check our formulas.
Right.
So the sum of the zeros is negative 2 plus negative 5,
which is negative 7.
which is negative 7. And according to our formula, negative b over a
Mm-hmm.
is negative 7 over 1, which is also negative 7.
Okay, so it checks out,
Yeah. And the product of the zeros is negative 2 times negative 5,
which is 10.
which is 10. And c over a is 10 over 1, also 10.
Okay, so the formulas hold true.
Yeah.
They work.
Did you?
And then example 3 looks at x squared minus 3.
Right, which we can factor as x minus square root of 3 times x plus square root of 3.
Okay,
So the zeros are square root of 3 and negative square root of 3.
got it.
So let's check again.
Okay,
The sum of the zeros is square root of 3 plus negative square root of 3,
which is 0.
which is 0. And negative b over a is negative 0 over 1, also 0.
Checks out.
And the product of the zeros is square root of 3 times negative square root of 3,
Which is negative 3.
which is negative 3. And c over a is negative 3 over 1, also negative 3.
So again, the formulas work.
They always do.
And then there's example 4 where the book gives us the sum and the product of the zeros.
Right.
And we have to figure out the quadratic.
Yeah, so it's like working backwards.
Yeah.
So let's say the sum of the zeros is negative 3
Okay.
and the product is 2.
Okay.
So we know that alpha plus beta is negative 3
Mm-hmm.
and alpha times beta is 2.
Right.
So using our relationships,
Mm-hmm.
we have negative b over a equals negative 3
Okay.
and c over a equals 2.
Got it.
And let's take the simplest case where a equals 1.
Okay.
So that means b equals 3 and c equals 2.
Right.
which gives us the quadratic x squared plus 3x plus 2.
Okay, so we found the quadratic.
Yeah, and the book points out that you could multiply that whole thing by any constant, like k times x squared plus 3x plus 2.
Where k is just any number.
Any non-zero number.
Okay.
And it would still have the same sum and product of zeros.
Oh, that's interesting.
Yeah, it's like a family of quadratics.
Okay, cool. So we can work both ways.
Yeah, we can go from the quadratic to the zeros.
Right.
And from the zeros to the quadratic.
Okay, that's powerful.
It is.
Now, what about cubic polynomials?
So those are the degree 3 ones.
Right. Are there similar relationships for their zeros and coefficients?
Yeah, there are.
Okay.
So for a cubic x cubed plus bcx squared plus cx plus d, and let's say the zeros are alpha, beta, and gamma.
Okay, alpha, beta, gamma.
Yeah, so we have 3 relationships.
Okay.
The sum of the zeros alpha plus beta plus gamma.
All right.
That's equal to negative b over a.
Okay, so that one's the same as the quadratic.
Yeah.
Okay.
The second one is the sum of the products of the zeros taken 2 at a time.
Okay, so like alpha, beta plus beta, gamma plus gamma, alpha.
Exactly.
Okay.
And that's equal to c over a.
Okay, C over A.
And then the third one is the product of all 3 zeros.
Alpha, beta, gamma.
Yeah, that's equal to negative d over a.
Okay, so it's negative D over A. Interesting. So there's like a pattern with the plus and minus signs.
Yeah, you see that?
Yeah. Okay, and then the book has an example, right?
Yeah, example 5. It looks at the polynomial 3x cubed minus 5x squared minus 11x minus 3.
Okay.
And it says the zeros are 3, negative 1, and negative 1/3.
Okay.
So first they check that those are actually the zeros.
Right, by plugging them in.
Exactly, making sure you get 0.
Okay.
And then they verify the relationships.
Okay.
So the sum of the zeros 3 plus negative 1 plus negative 1/3.
Yeah.
That's 5/3.
Okay.
And negative b over a is negative 5 over 3, which is also 5/3.
Okay.
The sum of the products taken 2 at a time is 3 times negative 1 plus negative 1 times negative 1/3 plus negative 1/3 times 3,
Okay.
which is negative 3 plus 1/3 minus 1.
Which is negative 11/3.
Yeah, and that matches c over a...
Which is also negative 11/3.
Right. And finally, the product of the zeros is 3 times negative 1 times negative 1/3.
Which is 1.
Which is 1.
Right.
And negative d over a is negative 3 over 3.
Which is also 1.
Exactly.
So the relationships hold true.
Yeah, they always do.
Okay, so this deep dive into polynomials, like we've gone from the very basic definition to like how they're classified,
Right.
how to evaluate them, what their zeros are,
Yeah.
both algebraically and visually, and then how those zeros are connected to the coefficients,
Exactly.
at least for like linear, quadratic, and cubic.
Yeah, we've covered a lot of ground,
We have.
but it's all connected.
It's pretty amazing. And so
Yeah.
for our listeners out there, like
Yeah.
these polynomials that might seem kind of abstract,
Yeah.
they actually have this like visual meaning
Right.
on graphs.
Yeah, like where they cross the x-axis.
Yeah, exactly. And the numbers that define them,
The coefficients.
yeah, they hold the key
They do.
to understanding the solutions.
The zeros.
Yeah.
It's a great example of how different points of math, like algebra and geometry,
Yeah.
they all kind of work together.
It's all connected.
Yeah.
Well, this has been a really cool exploration.
It has.
Thanks for taking us through it.
My pleasure.
Now, for all of you listening, we've talked about polynomials up to degree 3.
Linear, quadratic, cubic.
Yeah, so think about like what happens if you go higher.
Yeah, degree 4, degree 5, and beyond.
Yeah, like do those relationships still hold?
That's a good question.
And what do those graphs look like?
Yeah, they can get pretty wild.
Right, lots of twists and turns.
Yeah, it's definitely something to explore.
Yeah, keep that in mind as you continue your mathematical journey.
Absolutely.
All right, thanks for joining us for this deep dive.
Thanks for having me.
See you next time.